In this lesson, what we're going to do is to look at the physical and chemical properties of a class of molecules called the halogenoalkanes. Now, a halogenoalkane is going to be like an alkane molecule, but what it will have, at some point in the molecule, it will have a halogen connected instead of a hydrogen. So there we've got chloromethane. Could also have bromoethane. Both of these molecules would be examples of halogenoalkanes. So basically you could have any halogen atom connected. It could be fluorine, chlorine, bromine or iodine in one position here attached to one of the carbons. So the first thing we'll look at is the actual physical properties, things like boiling point, solubility, how well it mixes with water. And the key difference here obviously is the presence of this halogen, and the result of that is that these molecules are going to have a higher boiling point when compared to alkane molecules or alkene molecules of similar chain lengths. And the reason for that is that this bond is what we call polar. So whereas in an alkane you've got no polar bonds, here the chlorine is what we call more electronegative because it's on the very right of the periodic table. It's got a lot of protons in its nucleus and it pulls the bonding electrons across towards it, and so unlike the alkanes and the alkenes, what we have is a permanent dipole. So in the alkane molecules, something like, for example, methane, which would be just CH4, between methane molecules the only interaction would be van der Waals forces, which is where basically the electron cloud, the electrons in the molecule that are constantly moving around, at any one instant in time you might just find more electrons on one side of the molecule than the other, and when we get what we call an instantaneous dipole, which is very transient, it's not around for very long, that induces a dipole in a neighbouring molecule and you get this sort of this van der Waals interaction. But here we're not relying on that instantaneous and induced dipole. We've actually got a permanent dipole because of this polar bond, and that means that the interaction here between these halogenoalkane molecules is going to be that much stronger. Okay, so because of this polar bond here, these interactions between these molecules are going to be the permanent dipole forces that are going to be stronger than these ones. So it will have a slightly higher boiling point, but it's still not great. It's still not a strong interaction. It's still a pretty weak interaction. So for example, something like chloromethane here will have a boiling point of around about -24 degrees Celsius. It's going to be a gas at room temperature. The interactions here, although we've got a polar bond here, it's still that the permanent dipole forces that are going to interact between these molecules are still not strong, they're weak, and we're going to still have quite low boiling points. So at least the short chain halogenoalkanes are going to tend to be gases. And also, because this interaction is still quite weak, it's much weaker than the interaction that exists between water molecules. Now we'll talk more about this interaction later on, but the interaction between water molecules is something called a hydrogen bond, which is much stronger than these dipole forces that exist in these halogenoalkanes. So here, this interaction between these water molecules is much stronger, and if a chloromethane molecule here tries to interact with water, it forms a much weaker interaction than water would do with another water molecule, so it can't really interrupt the interaction, so it doesn't mix with water. The water molecules would rather form interactions with other water molecules than they would do with this methane molecule. So halogenoalkanes, two properties, still higher boiling point than an equivalent alkane and alkene because we've got slightly stronger intermolecular forces. but still overall, relatively low. But as I say, a little bit higher than the equivalent alkane or alkene. Second property, really very low solubility in water, doesn't mix with water, basically immiscible. So, the key physical properties then of halogenoalkanes. They've got a higher boiling point than an alkane or an alkene with a similar chain length, and that would be due to the dipole-dipole forces between the molecules, which are a little bit stronger than the van der Waals forces. And the other second property, they are immiscible with water. They're not going to dissolve in water. So what about the chemical reactions then of halogenoalkanes? Well, the first thing here is that they will react with nucleophiles. They will react, for example, if we put up a halogenoalkane here, let's go for chloroethane. They will react with water molecules, and they will react with water to form an alcohol. So this one would form ethanol. However, this reaction is extremely slow. It's quicker if instead of using water we reflux it with hydroxide ions, so sodium hydroxide, so we can achieve basically the same sort of reaction. We can form ethanol if we actually, instead of reacting chlorine in there, if we react this instead with hydroxide ions, again what we would form is an alcohol. Now the reaction conditions there are to reflux. So what does that mean? We use this sort of apparatus here. So we take our reaction mixture, which might be chloroethane, sodium hydroxide, and we heat it up. Because the reaction normally will be quite slow, if we heat it we can make the reaction go much quicker. But something like chloroethane will evaporate away quite easily. So what we do is we fit this condenser to it, and we have cold water here running through the jacket of the condenser. So as the vapour moves up the condenser, it condenses back into a liquid and falls back into this flask. So what we're effectively doing is repeatedly boiling and evaporating and then condensing the reaction mixture so it doesn't just evaporate away. So this repeated boiling and condensing of a reaction mixture we call refluxing. Simple as that. Basically it just allows us to heat the reaction mixture for an extended period of time to speed up the rate of reaction. Now the reaction here is what we call a nucleophilic substitution reaction, and that is the general class of reactions that halogenoalkanes will participate in. And again, it's due to the fact that this bond here is polar. Chlorine retains a partial negative charge, when delta here means partial, it's not a full negative charge. These electrons in this carbon-chlorine bond aren't fully transferred across to the chlorine, but they are pulled a little further towards the chlorine, basically by what we call the greater electronegativity of the chlorine atom, the stronger pull. Electronegativity is the strength of the pull that the atom exerts on the bonding electrons, the pair of electrons in that covalent bond. The chlorine exerts a stronger pull on them than the carbon atom, so it pulls those electrons a little bit closer to the chlorine and away from the carbon, and that causes this charge distribution here, this what we call this dipole. So what happens then is a hydroxide ion from sodium hydroxide comes in. Now the hydroxide ion has got a negative charge, OH minus, and it's got a sort of pair of electrons here, a lone pair of electrons, a free pair of electrons on that oxygen atom. And a nucleophile is an electron-rich species. Well, this is electron-rich, it's got a negative charge. And it's electron-rich species that then seeks out a positive centre, which is what this carbon atom is here. So what happens, that pair of electrons on that oxygen is attracted to that positive centre there, and it starts to form a bond. So the curly arrow again shows the movement of a pair of electrons and that pair of electrons is starting to form a bond into that positive or partially positive carbon atom. At the same time, because of course carbon can only form 4 bonds, the carbon-chlorine bond can break. Now the actual reaction mechanism is a little bit more complicated than this, but really this is all we need to know. And what will happen here is we will start to form a bond here to OH. We break the carbon-chlorine bond, so we obviously will get the alcohol. So we've got an OH group on there, and of course we'll get our chloride ion. So that is the reaction mechanism. So the first real reaction we've got here is refluxing a halogenoalkane with hydroxide ions. Usually use something like sodium hydroxide to give you hydroxide ions, and you will form an alcohol. So what other reactions could we have here? Well, we could have, for example, a reaction between a halogenoalkane and ammonia. Again, this is a polar bond. This carbon will be partially positive, this bromide will be partially negative. I can indicate that on if you want. Delta plus, delta minus, we've got the dipole there. What we're going to do is react this with ammonia, and basically the ammonia molecule acts as a nucleophile. So basically there's a lone pair of electrons on the nitrogen which can actually be attracted into this positive centre. At the same time the carbon-bromine bond will break, and basically what we will form is an amine. So what we'll do is we'll get that. The ammonia loses a hydrogen after it attaches here. Basically we'll get HBr. So that is the reaction that occurs with ammonia. The thing is, this amine that we formed here can then also act as a nucleophile and can also attack this carbon centre. So what you can have now is further reactions. So our amine can also react basically. Again, the pair of electrons on the nitrogen can act and attack this positive, partially positive carbon here. We eliminate, or we substitute basically this in for the bromine. So what you could end up here with is this molecule, and potentially that could also act, and you could actually replace that hydrogen as well with another CH3, CH2 as it reacts with another halogenoalkane molecule. Okay, another reaction that halogenoalkanes will undergo is the reaction with cyanide ions, Cn-. So generally here, these reaction conditions, we would probably something like reflux the reaction mixture. So reflux the halogenoalkane with, for example, potassium cyanide in ethanol. So if you use potassium cyanide in ethanol, provide these cyanide ions, and you reflux that reaction mixture, so repeatedly boil and condense it, the Cn- ions would again act as a nucleophile and would attack this partially positive carbon centre, and you would substitute basically the Cn- ion for the chloride ion. And what you would end up with then, quite simply, is this molecule. Now that's called a nitrile. And in organic chemistry, that's a very useful reaction because you're actually extending the length of the carbon chain. You can see that whereas we had 2 carbons, we've now got 3 carbons in that chain, and then you've got a bond to the nitrogen there. So we would call that propane nitrile. And there we go. Again, nucleophilic substitution, this time substituting the chloride here for a cyanide. We've talked about nucleophilic substitution reactions and the halogenoalkanes, which is the main class of reactions that the halogenoalkanes undergo. However, it is possible to use for an elimination reaction to take place as well. So we've talked about refluxing a halogenoalkane with aqueous sodium hydroxide. So if your sodium hydroxide is dissolved in water and you reflux it with the halogenoalkane, you'll have a nucleophilic substitution reaction in which the hydroxide ion replaces the bromine. However, if instead of having the sodium hydroxide aqueous, you have sodium hydroxide in ethanol solvent and you heat it, what will happen is the hydroxide ion can then act as can then cause an elimination reaction. So basically what happens is the hydroxide ion sort of attacks that hydrogen there, and the pair takes away that hydrogen, and the pair of electrons in the carbon-hydrogen bond is used to form a double bond here between these carbons, and you eliminate this bromine here. And so basically what you get is an alkene. So it is possible to actually form an alkene from a halogenoalkane. We'd also get there bromide ion, and we get water. Okay, so basically the key reaction with the halogenoalkanes are nucleophilic substitution reactions, but it is under certain conditions, basically if the sodium hydroxide is in ethanol instead of water, we can get an elimination reaction to form an alkene. So that's just something to bear in mind.